In this video, I want to take a look at using row operations to calculate the determinant of a 4 by 4 matrix, and then discuss why this might be more efficient to do it this way than to do it by the cofactor expansion method. So anyway, I've got a determinant here, determinant of a 4 by 4 matrix, and what I'm going to do is I'm going to do row operations and keep track of what that effect it has on the determinant. So the first thing I'm going to do, going from here to here, is I'm replacing row 2 here with row 2 minus 5 times row 1. So I've got 5 minus 5 is 0. I've got 6 minus 10 is negative 4. 7 minus 15 is negative 8. And 8 minus 20 is negative 12. So there's that row there. Now what I did was I added a multiple of row 1 to row 2 that does not change the determinant, and so I have an equal sign here. Right? These two rows stayed the same. Now, when we did row operations before, I was always careful not to put equal signs. I was putting arrows saying this matrix gets transformed into that matrix. But at this point, I have determinants of matrices, and the determinants of this matrix is the same as the determinant of that matrix. So these bars are saying this determinant equals that determinant, and there really is an equal sign in here now. Okay, so no change in the determinant by that row operation. The next thing I'm going to do is, let me make it a little bit smaller, is I'm going to replace row 4 by row 4 minus 2 times row 1 to get this. Again, that row operation has no effect on the determinant, and so this determinant is equal to this determinant, equals this one. Okay. Next, I'm going to get a 1 right here by factoring out a negative 4 from that row. Well, the negative 4 just comes out in front. That is, if I look at it this way, this matrix right here was obtained from this one by multiplying this row by negative 4. So this determinant is negative 4 times this determinant. So you factor out that negative 4, it goes out in front. Likewise, I want to factor out this negative 3 right here. I guess I don't have to do that, but I'm choosing to do that just because it makes my calculations easier later, I guess. So I see that I have a factor of negative 3 in every one of these, and so I pull it out in front, making this just a 1, 2, 4. Okay. Now I'm going to do some things like, what am I going to do? Row 3 is going to be row 3 minus 2 times row 1 to get this. And I did row 4 is row 4 minus row 1. Each of those things is adding a multiple of one row to another, does not change the determinant. So this stuff stayed out in front, this determinant is the same as that determinant, and I've got an equal sign here. Now I've got it to the point where I've got a diagonal matrix, not a diagonal matrix, an upper triangular matrix. And the determinant can be seen just by multiplying along the diagonal. I've got 1 times 1 times minus 1 times 1, that's this minus 1, for a grand total of negative 12. In fact, I asked my calculator to do this for me, and it did get the same answer of negative 12. I just turned it back on and looked, and yes, I got negative 12. So you might say, yeah, but it's a lot of work to do row operations. How much work? How much work is it really? If you've got an n by n matrix here that you're trying to take a determinant of, how much work is it to do it the cofactor expansion way? Well, the cofactor expansion way ends up being a sum of those elementary matrices. Sorry, not elementary matrices, elementary products. Right? And so the question is, how many elementary products are there? Well, I think we determined in a previous video that there's n factorial elementary products, right? N factorial gets really big really fast. I mean, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, 24 times 5. All of a sudden I'm feeling like turning my calculator on. 24 times 5 is 120. Then multiply that by 6 for 6 factorial is 720. And, times 7. is 5,040. This grows very, very quickly. And so essentially, if you're thinking about an algorithm, a computer algorithm that calculates determinant, the number of steps that you're going to have to take doing it this way, doing the cofactor expansion, is somehow related to n factorial. This gets very big very fast. Okay. On the other hand, if you look at an n by n matrix and say put it into row echelon form, how many steps does that take? Well, essentially you have, the first thing you're going to do is you're going to get a 1 in that upper left corner if you can, right? And how many steps might that take? Well, you might have to take whatever's there and divide the whole row by it. Well, that would be n steps, right? And then you say, well, how about getting, zeros underneath here? Well, to get zeros underneath there, you're going to have to add multiples of this row onto each of those, which might be n calculations to get one row and then n calculations to get the next row. So that would be like n squared calculations. But then you got to do that for the next spot and the next spot and the next spot. So at worst, you have to do that n times. Now it's actually a little better than that. That calculation to get a 1 right here and then zeros underneath it, you say, well, then just repeat it for each row n times, but it gets actually faster each time. So the worst case scenario here is something on the order of n cubed, right? This is on the order of n cubed. Let's not say equals, but it's so n cubed grows like 1. 2 cubed is, so 1 cubed is 1, 2 cubed is 8, 3 cubed, I should be able to do this quickly, right? 27. So initially it looks pretty bad, but 4 cubed is 64. So still we're better off with this one on a 4 by 4. 5 cubed is 125. Well, that's still better there, I guess, right? 6 cubed is 4,000. Oh, sorry, that was 6 to the 6th. I wanted 6 cubed is 216. So already that's much better. And 7 cubed is 343. So although it started off looking worse, it's definitely better in the long run. That an algorithm that's n cubed time is so much more efficient than one that's n factorial time. So using these row operations is going to save us a lot of time in the long run. I agree, small ones, probably not. You want to just do the cofactor method. But as the matrices get bigger, you're going to want an algorithm that uses far less times and less steps. So row operations is the way to go.